Welcome to The Explainer. Today, we're diving into the absolutely fascinating, kind of heroic story of the hardware that actually powers our connected world. I mean, we use it every single day, right? To stream, to chat, to work. But the invisible infrastructure making all of that happen has a history completely filled with chaos, totally groundbreaking engineering, and massive paradigm shifts. Let's get into it. So imagine this for a second. An internet where literally everyone in the world shares a single cable, and you just have to wait your turn to speak. Sounds like a total nightmare, right? Well, that chaotic scenario was actually the reality of early 1980s Ethernet. At the time, networks basically operated as a giant party line. Everyone shared the exact same physical wire, and if two machines tried to transmit data at the exact same millisecond, bam, their signals would literally crash into each other on the cable. Because of this collision, both machines had to stop, wait a totally random amount of time, and then try again. As you can guess, when they added more computers, the traffic jams became completely overwhelming. To wrap our heads around how we fixed this huge problem and built the networks we use today, we use a conceptual framework called the OSI model. It's like a blueprint. It has 7 layers, starting from the physical wires at the very bottom, all the way up to the application software at the top. But for this explainer, we're going to focus entirely on the bottom 3 layers: physical, data link, and network. This is the hardware basement. This is where the magic literally happens. All right, section 1, the early network chaos. We're starting with thick cables and taps. Back in the day, the landscape was vastly different. Computers were incredibly slow. We're talking low megahertz range here, and memory was astronomically expensive. And to connect these clunky machines, technicians had to use these massive, thick, half-inch coaxial cables. They couldn't just plug in a simple, friendly little jack either, no way. They used what were notoriously called vampire taps. A technician literally used a tool to drill right through the outer and inner shields of a live cable just to bite into the central copper wire. It was difficult, it was messy, and it was severely limited by distance. Now, you might know that electrical signals naturally weaken as they travel through a copper cable. So when signals started dying over longer distances, engineers turned to layer 1 of the OSI model, the physical layer. They brought in devices called repeaters and hubs to solve the problem with sheer brute force amplification. A repeater basically just regenerates a weak signal so it can travel a bit further. But there was a massive downside here. They were essentially dumb devices. They passed absolutely everything through. And yeah, that included all of that awful collision noise we talked about earlier. And you can see exactly how this problem plays out. A repeater just connects 2 segments of a local area network entirely blindly, without doing any filtering whatsoever. Because it's literally just copying bits from one side to the other, the 2 connected segments basically behave as one incredibly long, noisy collision domain. Every single machine on both sides still has to sit there and wait its turn to speak. Not great. But here's a crazy thought. We actually still use layer 1 repeaters today, they're just vastly upgraded. Modern fiber optic repeaters use that exact same fundamental dumb concept. Devices like Pearl's fiber mode repeaters use what's called a 3R signal regeneration process. They retime, reamplify, and reshape the light signals to blast pristine data across up to 160 kilometers or 100 miles of glass fiber. They are protocol independent, meaning they just blindly pass the light forward. That is absolutely perfect for sheer distance, but as we know, it still doesn't solve traffic congestion. Which brings us to section 2, how bridging saved Ethernet and the rise of smart hardware. As networks kept growing throughout the 1980s, those shared cables just got way too noisy. The delay and the sheer variance in transmitting data were going through the roof. Ethernet desperately needed saving. Enter the Digital Equipment Corporation, or DEC, and specifically 2 brilliant engineers, Alan Kirby and Mark Kempf. At this point, Ethernet was evolving from 3 megabits per second to a shiny new 10 megabit standard. To bypass the physical limits of those noisy shared cables, Kirby and Kempf realized they could build a device to store and forward the packets of data. Kempf actually built a prototype of this in under a year using a Motorola 6800 processor. And get this, he had to fiercely defend that specific hardware choice to senior executive Gordon Bell. Kempf had to argue against a super strict company mandate to use DEC's own internal T11 chip. And he actually won the argument simply because the Motorola processor made the internal transfer costs cheaper and actually viable, a real game changer. If you look closely here, you can see the exact leap from dumb layer 1 hardware to smart layer 2 hardware. Look at the shift. A repeater passes everything, right? But a bridge, which operates at layer 2, the data link layer, actually examines the destination of the data. It filters the traffic. It only forwards data across the segment if it absolutely has to. Here's how that filtering looks in action. By looking at the destination MAC address, that unique physical address burned right into your network card, a bridge actually builds a little table. It learns which side of the bridge a specific computer lives on. So if computer A talks to computer B and they're on the same side, the bridge just blocks that traffic from crossing over. It smartly keeps local conversations local, completely saving the broader network from all that unnecessary congestion. Moving on to Section 3, Preventing Disasters, using the Spanning Tree Protocol. Now, this new smart hardware was undeniably a massive breakthrough, but it accidentally created a terrifying new crisis. If you plugged multiple bridges together in a way that created a physical circle, you inadvertently created an infinite loop. The bridges would forward the exact same packets back and forth forever and ever, completely melting down the entire network in what's called a broadcast storm. They desperately needed a safety mechanism before they could even think about deploying this globally. And the visionary architect Radia Perlman, who was also working at DEC, answered the call. She invented an incredibly elegant algorithm called the Spanning Tree Protocol. It essentially allowed the bridges to automatically map out the entire network and mathematically block those redundant paths. It prevented the loops while keeping backup paths in reserve just in case. As Alan Kirby himself noted, her invention fundamentally saved Ethernet from destroying itself. Section 4, Layer 2 versus Layer 3. Let's see how this all builds as we move further up the OSI model. Because eventually the technology of the original 2-port bridge evolved. We moved from devices with just 2 ports to massive multi-port switches, dedicating a single unshared wire to every single computer. And eventually the networks got so big we had to move even further up the OSI model to Layer 3, the network layer. To really grasp this jump, try thinking about it like this. We can think of a Layer 2 switch extending a single network, kind of like your local postal worker. It delivers messages directly to MAC addresses inside a single building. But a Layer 3 router, that's like the massive cross-country sorting center. It connects fundamentally different networks together, routing packages using IP addresses across entirely different cities and even different network protocols. But hey, technology rarely sits still, right? Over time, enterprise switches got so incredibly advanced that they started borrowing capabilities straight from routers. Thus, the Layer 3 switch was born. By using highly specialized chips called ASICs, Layer 3 switches can route IP addresses internally via hardware switching. This gives them lightning-fast speeds without all those traditional, slow software processing hops that a standard router would normally require. So the absolutely crucial point here is that choosing your hardware completely depends on what you actually need it to do. If you're just interconnecting devices in a pure, local domain, a standard Layer 2 switch works perfectly. But if you're aggregating multiple networks, if you need advanced security, or if you require lightning-fast inter-VLAN, IP packet switching, well, you have to upgrade your architecture to a Layer 3 switch. And finally, Section 5, Building the Global Internet. Let's wire the world together. We've zoomed way in, but now let's zoom out. We've gone from a single messy copper wire to smart bridges, all the way to high-speed Layer 3 switches. Now we look at how all these repeaters, switches, and routers actually wired together into the ultimate global architecture. A quick terminology check here because it's super important. An internet with a lowercase I simply means any private network of distinct networks that are connected by routers. So your local school or office, that's its own small lowercase internet. But the moment your local router gateway passes that traffic out to the outside world, you enter the internet with an uppercase I, the massive global public network that relies on shared routing protocols. The sheer speed of human innovation here is honestly staggering. Today, we've gone from those early 3 megabit vampire taps that Alan Kirby worked so hard to replace, all the way to 800 gigabit coherent optics, powering modern AI data centers. We are literally pushing nearly 1 trillion bits a second across single optical paths using these evolved switching principles. It's wild. Which leaves us with a totally fascinating, almost philosophical paradox directly from the pioneers themselves. Modern Ethernet operates on dedicated switch ports. It has completely 100% stripped away the shared media, the half-duplex transmissions, and the collision detection that originally defined what Ethernet actually was in the first place. So, Has Ethernet evolved so much that we are literally just using a legacy brand name for a totally different technology? Or is the core abstraction still the same? It's a pretty profound question to ponder the next time you plug in a network cable. Thanks for joining me on this explainer, and keep questioning how our world connects.